Okay, here's your acids and bases test review. Okay, acids. Two theories for acids. You've got Arrhenius, this guy, and you got an alternate theory, which is Bronsted and Lowry, or BNL. Okay, they basically both try to define what an acid is. Arrhenius is the one that you really care about. He says that acids start with an H. They produce H plus or H3O plus ions in solution. It's the only positive ion in solution. Okay, so something like HCl, HI, HBr. All of those are Arrhenius acids. H2SO4, H3PO4, Arrhenius acids. They all start with H's, okay? Arrhenius acids and Bronsted and Lowry acids are basically the same thing, but the alternate theory kind of defines them differently. And Bronsted and Lowry defines an acid as a proton or an H plus. It's the same thing, remember? H plus is a proton donor. So that means they donate protons when they are dissolved. So here's an example. HCl plus water. HCl is an acid, and acids do this special thing called ionizing. That means that covalent bond that's there is actually broken, and you form two ions. So it donates the proton. Here's the H. It's going to donate it to water, and it's going to become H3O plus. Oh, look at this. Here's my H3O plus, okay? Plus Cl minus, okay? Another way that you could look at that is like this. HCl is ionizing in water to H plus and Cl minus, okay? Either of those are fine. In this case, this top case, you can see that HCl is losing a proton and water is gaining a proton. Water goes from H2 to H3O plus. It gained an H plus. Therefore, water is acting like a base. Okay? This is the ionization of HCl. And this is why it's an electrolyte. Okay? So acids are electrolytes. Additionally, if you're looking for acids, you're going to look on Table K. Table K in your reference table gives you a nice list of all things that are acids. It's very, very helpful. Take a look at Table K. Okay? It's just a list, but it gives you everything that's an acid. So if you know you're looking for an acid because you're producing H3O plus or H plus, start with Table K. Remember, acids start with an H, and they ionize in solution. That means they fall apart into ions. Okay? Bases. All right, I have enough room, right? Bases. An Arrhenius base produces OH minus ions as the only negative ion in solution. It's going to give you an OH minus. So something like NaOH is an Arrhenius base. LiOH is an Arrhenius base. Okay? Remember, CH3OH is not a base. Anytime you have OH with carbons and hydrogens in front of it, it's not a base. So start by looking at your reference table, Table L. And I'll write that down here where the one is for acids. Okay? Bases are also an electrolyte because bases do what we call dissociation. That means NaOH is going to fall apart into the ions that make it up, the ions that you flip-flop, so Na plus and OH minus. Okay? These floating charged particles, mobile charged particles, make bases electrolytes as well. Okay? All right. The other theory that describes bases describes a base, Bronsted and Lowry describes a base as a proton acceptor. That means they can take protons out of solution. So here is a great example. NH3, according to Table L, is a base. When you mix it with water, it's going to form NH4 plus and OH minus. Here's my OH minus from Arrhenius, and here is my NH3 gaining a proton from the water and turning into NH4+. Now, if you compare what we just did, I'll write this back over here. I don't know why I erased it. Cl minus. Here, water's behaving like a base. Here, water's behaving like an acid. Water's what we call amphiprotic, meaning it's both an acid and a base. A and B. What are you looking for things that are amphiprotic? You're looking for something like water, H2O. You're looking for HSO4 minus. This is what happens when H2SO4. Okay, let's start that again. So we have HSO4 minus, okay, is what happens after sulfuric acid loses a proton, okay? It can also lose another proton. This is the one right here it can lose. It can also gain one and go back to sulfuric acid. So it can go both ways. What else you're looking for is like H2PO4 minus or HPO42 minus or HS minus, okay? They're all minus, okay? So they can all gain a proton and become neutral. This would become, this could become H2S. This one would become H3PO4, and this one would become H2PO4 minus. They're all capable of gaining a proton and losing a proton, okay? So that makes them amphiprotic. Finally, salts. What are you looking for a salt? Something that's ionic, something that has no H plus and no OH minus. It's got to be ionic, and it's got to have H plus and OH minus, okay? So you are looking for something like CaCl2 or Na2SO4, okay? They don't have hydrogen ions, they don't have hydroxide ions, so those are going to be a salt. They're going to have little effect on the pH of the solution. Acids, bases, salts. Okay. Let's go back to full screen. All right, titration problems. I'm going to spend very little time on this because you already know this. We did this in lab. You know your titration formula is molarity of the acid times the volume of the acid equals molarity of the base times volume of the base, okay? So that is your titration formula. If you have one unknown, you can solve for the unknown given the other three. How do you know when to use this? You know to use this when you're doing a titration. You know to use this when you're doing a dilution, okay? And you know to use this when you have two molarities or two volumes, okay? Something like the molarity formula, which is moles per liter, you only have one molarity and one volume, okay? This one you have 2 and 2, and you're not actually looking for moles of anything. The hardest part of this formula is when you have a diprotic acid or a base with 2 hydroxides. So if I'm going to titrate something like sodium hydroxide and sulfuric acid, okay, I have a 2 here and I have a 1 here. I have 1 hydroxide and I have 2 hydrogens, okay? So when I plug it in, let's say that I have 0.1 molar and 25 mils, and I have, what's the concentration of acid if it takes 30 milliliters here, okay? The side that's got the 2 gets multiplied by 2. So when I set up my formula, I'll do this in another color. I'm going to have 0.1 molar times 25 milliliters, okay? And 30 milliliters of acid times the molarity of the acid. Now my acid has 2, so I'm going to multiply that by 2. That whole side gets multiplied by 2. Here's my calculator. 0.1 times, that's divided by 0.1 times 0.1 times 25 divided by 60. I should get I'm not good at this. This calculator's not working. I get 0.042 molar for my molarity of my acid. Okay? All right. That's the key. If this was H3PO4 and I had a 1-to-3 ratio, then this would not be multiplied by 2, it would be multiplied by 3. Okay? So whatever, you got to make sure when you're doing titration problems, you are looking and making sure that you see whether you have a NaOH with H2PO4, maybe you have NaOH with HCl, and that's 1-to-1. You don't have to worry about it, okay? Maybe you have calcium hydroxide with HCl. In that case, you have 2 hydroxides, so the base side gets multiplied by 2, okay? That's titration. pH. The things you need to know about pH, these 2 formulas. You need to know that pH is the negative log of your H plus concentration. And you need to know that pH plus POH equals 14. And you probably should know that POH, which you'll be asked about much less than pH, equals the negative log of your OH minus concentration. It is super duper important to keep this and this straight, okay? I will give you a question where I say, if your hydroxide concentration is 1 times 10 to the negative 8th molar, what is the pH? A lot of you would just take that and take the negative log of 1 times 10 to the negative 8th, you would get 8, and you would say that that's the answer. Guess what? This is multiple choice, and that's an option. It's not the right answer, though. Okay? If I take the negative log of 1 times 10 to the negative 8th, I'm taking the negative log of my OH minus. This is my POH, so I get that my POH is 8. To find the pH, I say that pH plus POH equals 14, okay? I know that POH is 8, okay? And therefore my pH equals 6, okay? Make sure you're looking for that. If you're negative logging your OH minus, you're getting POH. If you're negative logging your H plus, you get pH. To go backwards, to get the OH minus concentration, you do 10 raised to the negative POH power. And to get the H plus concentration, you do 10 raised to the negative pH power. Okay, so be comfortable going back and forth. Make sure you use your parentheses, okay? Also important to know about pH is that as your OH minus concentration goes up, as this goes up, this goes down because they always equal this constant 1 times 10 to the negative 14th. These formulas are not on your reference table, but hopefully they are easy to remember. That pH is the negative log, and you know that 14 is your magic number, okay? Hopefully you also know that acids have a low pH, okay? That means a pH below 7. And bases have a high pH. Its pH is above 7, okay? Finally, I'll erase this. There we go. You need to know that every increase by 10 in concentration, okay? If this is my H plus concentration, it's going to be my change multiplied by 1, by 10, by 100, by 1,000. Here's my H plus concentration. Here's my pH. As my H plus concentration starts at, let's say, 10 to the negative 7th, 1 times 10 to the negative 7th, my pH here is 7. If I increase that by a factor of 10, 10 to the negative 6, my pH goes down 1, okay? If this becomes 10 to the negative fifth because it's increased from this initial by 100, my pH goes down 2. And 10 to the negative fourth, my pH is going to be 4. So my pH here is decreasing as my OH, as my H plus is increasing. Okay, remember that 10 to the negative seventh is a tiny number. 10 to the negative fourth is bigger by 1,000 times. It's 1,000 times bigger. So as my H plus concentration increases, it becomes more acidic, and my pH goes down. Okay, so each factor of 10 is going to be one step in pH. Make sure you keep that straight, and when you see those questions, take your time. Okay. The last thing I need to talk to you about is the indicator table, table M. Okay, table M. Make sure you understand how to read this. Okay, so it's going to tell you something, and I'm going to make this up a little bit. It's going to tell you that phenolphthalein has a color change from 8 to 9 of colorless to pink. What this means is that phenolphthalein below 8 is colorless. Okay? Above 9 is pink. Forget about the middle. You will not be asked about the middle of the range here. You're always going to be asked about the outsides. So it's colorless before 8, and it's pink above 9. So don't think things have to meet in the middle. We use this stuff in lab. Remember how it turned that faint pink? Remember how it was so hard to keep it around? It was so hard to pay attention. And is it this color pink okay? Is this color pink okay? It's hard to tell there in the middle, so you're not going to be asked about it. Phenolphthalein in an acid is going to be colorless. Phenolphthalein below 8 of pH is going to be pink. Is going to be colorless. Phenolphthalein in a pH of 6 is colorless. And a pH of 10 is pink. Okay? Remember, you're looking for the outside of that table. Good luck.